All right. So last time, which is Wednesday, I talked about Fourier analysis on the circle group. Okay. So what we did was proved Fourier's theorem, which shows that the characters are this z going to z to the n, e to the I theta going to e to the I n theta, where n is an integer. And then we showed that the span of those is dense in the space of continuous functions with sup norm, and consequently also dense in L2 with the L2 of t with the L2 norm. So they give an orthonormal basis. So that we proved, and so this proof is a nice one using the Fourier kernel. And then finally, okay, that no need to recap the proof. So I also indicated why the Dirichlet kernel doesn't work. So this we saw. Okay, finally, uh, we came to, I just quickly defined the Fourier transform. So for functions which are in L2 of the unit circle, you can define the Fourier transform. It's a function on characters, right? So just like in the finite case where you have a function on the group, then you have a function on the dual group, which is the set of characters. Here I have not talked about the group structure of the characters, but let's say anyway, the characters are indexed by integers. So that's why I'm writing Z. So this Z is to be thought of as the set of characters. So, so the Fourier transform is defined as f hat of n equal to f inner product with the corresponding character en, which is e to the in theta, which is given like this, f of theta e to the minus in theta d theta over 2 pi. And because it's an orthonormal basis, we have this expansion that you can write f as the linear combination. It's an infinite linear combination, so it's only meaningful in the limiting sense in L2. So you take partial sums of this side, then it converges to the left side f in L2 of t. That was a consequence of Fourier's theorem. So we have f inner product en, which is f hat of n en. So this is the recovery formula. So this is Fourier inversion. This is defining the Fourier transform in terms of the function. This is recovering the function in terms of the Fourier transform. And then we have directly from general orthonormal expansion, we have the fact that L2 norm squared of f is the sum of squares of the coefficients, which is, you can write f hat being a function on z, you can write f hat of L2 norm squared in L2 of z, which is z is endowed with counting measure. Okay, no normalization, of course, counting measure. Or more generally, inner product of two functions in L2 of t is inner product of the corresponding Fourier transforms in L2 of z. So this is what I ended with. All this whole thing comes directly from the basic Hilbert space theory, that if you have expansion with respect to orthonormal basis, then this kind of stuff is true anyway. Okay, so this we have seen. Okay. Now, what? Okay, one small point is that it looks a little different from the finite case, where on one side, if you look at Fourier inversion, Fourier transform is defined by an integral. Fourier inversion has a sum. They look a bit different. Unlike in the finite case where both were sums, here one is an integral, the other is a sum. Also, if you look at Planck-Stekel relation, on one side we have L2 of t, which is again an integral, and here we have L2 of z, which is a sum. So it's slightly different. The point is, this is, so I had mentioned when we were talking about the finite Fourier case also, although g hat is isomorphic to g, there is no canonical isomorphism, so it should be thought of as different from g. G double hat is equal to G, that is okay, but G hat should not be confused with G. It is better to treat it separately. And that becomes more apparent here because the set of characters of T is going to be indexed by integers. We will now investigate this point a bit more. Z itself is a group under addition, that's what comes, and its dual is going to be T. So the dual is not even isomorphic to the original group. That will not be the case in general. Okay, so in finite case, they were isomorphic, but not naturally. But here in general, they are not even going to be isomorphic. So just to clarify that picture, what I thought I would do is do Fourier analysis on integers. It's a simple thing. Usually nobody writes it, but it clarifies certain things and some features come out actually. So when we go to Fourier analysis on the real line, we will see that some of these features are already seen in Fourier analysis on Z. But before going to that, I want to mention a couple of things about Fourier transform on the circle itself. Two other points to note. Uh, so two or whatever. So some points. So if you look at the definition of the Fourier transform, f hat of n is f inner product n. Why does this integral exist? Okay, so it's if you look at this integral, the natural domain is not L2 functions. Okay, so will the integral exist? Yes, it exists. For in a moment you will see. I mean, or you may already see. So for definition of Fourier transform on the circle group is not L2 of Z, L2 of T, but L1 of T. Why? Because for f in L1 of T, define f hat again as before from integers to complex numbers by f hat of n is integral over the circle f of e to the it and then e to the minus int dt over 2 pi. If you see, this is the same formula f of theta e to the minus sin theta d theta over 2 pi. Only I don't write any inner product. Okay. The point is inner, of course, if f is not in L2, we shouldn't write it as inner product. But the point is En is bounded. Because of that, this integral exists. Right? It exists because it's absolutely integrable. If you put absolute value inside, this is 1 and f is integrable. So it makes sense. So this is well defined. So this is well defined. Because it's equal to 1. This integral is equal to 1, in fact. So it's well defined, and in fact, we can, for later purposes, we can see that it is bounded. F hat of n is less than equal to integral over t f of e to the I theta. If I put absolute values inside d theta over 2 pi, which is by definition the L1 norm of f. So that is, you can write f hat. It's something similar to what we have seen. L infinity of z is less than equal to f L1 of t. So that is one point. In fact, we can go further. So, but L2, okay, so because this is a finite thing, okay, so another point is that what about L2 functions? Will this integral exist for L2 functions? Because this is a finite space, finite measure space, L2 is contained in L1, right? Hence, this is an extension of the Fourier transform. So rather than just for L2 functions, which was how we were thinking orthonormal basis and such things, what we have is that we can define Fourier transform for L1 functions. But we have not said anything about recovery and stuff like that for a moment. Okay, so we have not said anything like a Fourier inversion modes. This may or may not make any sense. It may not, it's so caution, maybe I put a caution there. We have not said several things. One, what is the range of the Fourier transform? On L1 of t. Okay, we have not said that. I mean, we haven't said which functions on the integers arise as Fourier transform of L1 functions. When it was L2, it was L2 to L2 of Z. Every function in, I mean, that's kind of clear from here. Maybe I will later remark. If it was not clear, you can also go back. Any L2 of Z function you can put here and obtain an L2 of T function. Okay. So, whereas, so this is in contrast to the fact that L2 of T to L2 of Z is an isometric isomorphism. Okay, so here we don't even know which functions arise as L1 functions. Two, we have not said if, okay, so we have not said if f can be recovered from f hat. The answer is yes. Yes, it can be recovered from f hat. In other words, that is Fourier transform from L1 of t to, it maps into, we don't know the exact range, but we know that it maps into functions on Z which are bounded. Okay, at least L infinity. Let's just for the moment write L infinity of Z is injective. I have not proved this, but I'm just mentioning it at the moment. It is true. So first question, by the way, will have no good answer. We don't know exactly. To my understanding, we cannot specify what functions are Fourier transforms of L1 of t. It's complicated. So another third point is, yes, it can be recovered, but Fourier inversion does not hold. That is, we cannot write, we cannot take f hat of n en from minus n to n converges to L1 of t in L1 of t to f. Is this true? This is false actually. This is a false statement that if you take these partial sums and just replace L2 by L1 just like we had earlier, that's not going to be true. Okay, so this is not true. Nevertheless, in principle, f can be recovered from f hat. Fourier inversion formula doesn't hold. Okay, so these are some points to keep in mind. Okay, any questions, comments? Okay, one more further extension can be made. I will just make it here. That we can even go further. Okay, I am saying going further. If mu is a finite Borel measure, on T, define its Fourier transform as, we just define its Fourier transform like this. It's a function again from integers to complex numbers, defined as mu hat of n is integral with respect to mu of en. Means you can define this. It's a finite Borel measure. So this is a bounded function. You can certainly integrate it with respect to a bounded, with respect to a finite measure. So this is called the Fourier transform of mu. So why do I say going further? In what way is it going further? Is it really going further? Well, if f is in L1 of t and f is non-negative, then we can associate it to a measure. We can think of it as the density of a measure. Is a finite Borel measure. And the two definitions coincide. Mu f hat of n is same as what I had defined as f hat of n. For L1 functions, we defined f hat by just integrating f of e to the I theta e to the minus I n theta d theta over 2 pi. For measures, we defined here. But if f is the density of the measure mu, they are the same, right? Because what is d mu of theta? It is f of theta d theta over 2 pi. So if you put it, you see that they are the same. So in that sense, this is an extension. Okay, strictly speaking, not an extension, because here you need non-negativity to make it a, because for me measures are positive measures. If you really want to say extension, you have to consider general complex measures, which are nothing but of the form mu1 minus mu2 plus I mu1 minus I mu3 minus I mu4. I mean, if you know the Jordan decomposition, we can talk about complex measures, which are just linear combinations of positive measures. Then we can say it is really an extension. But I don't want to get into this issue. When I consider measures, it will be positive measures. But in this sense, it is an extension from measure functions to measures. So you don't even need functions to define Fourier transform. You can define it for measures also. One can even go further, but this is where I will stop. Okay, any questions, comments so far? Is it okay? Okay, so if not, okay. So now let me go back then. So many of you may have seen many of these things. Okay, I don't know. But anyway, so I want to now clarify a bit about this dual and business. Later, I will just mention the story in the general sense of locally compact abelian groups. Then it will become more clear if I say it now. So when I say it, dual of circle group is integers and dual of integers is circle group, I should study Fourier analysis on integers first. Then we will see the inversion properly, right? So that's what I want to do quickly. Fourier analysis on integers. This is actually a triviality more or less, but still there are features which are something to pay attention to. Okay. So now let's look at Z as a circle. Z with addition. Sorry, not circle group, Z plus. It's a group. Yeah, it's with the discrete topology actually, but okay. So what are the characters of this? So if I have a homomorphism from so character means we have to consider homomorphism into the circle group, right? So what are the possibilities? Then the only thing I have to pay attention to is because this is a cyclic group, so it is cyclic. So I only need to pay attention to where the one generator goes. So chi of 1 is some e to the I t for some t in 0 2 pi, right? So then I also have fixed chi of n for all n. It is e to the int for all n in integers. There is no other choice. If one has to go to that, n has to go to this. So, and this is in fact also this does define a also for every t. This does define a character. I mean, this is a homomorphism. So we'll call it, let's call it EV e to the IT or just for simplicity, evaluation T. What I mean is, the reason why I'm writing that is, it's like the evaluation maps that I was thinking of earlier, is the evaluation of this En at e to the it. En is the character of T. En is the character of T which takes z to z to the n. So this is the evaluation at e to the it. So that's why I call it, I just am for the moment denoting this. So hence z hat is identified as a set with T, because for every element of the circle group there is one character of z, and so as a set it can be identified as the circle group. Okay, so that's what characters of z are. So how would you define Fourier transform of functions on z? But one of the things to notice is, so these characters are not orthonormal. So characters are not in L2 of Z. So in fact, they are not even in L2 of Z, right? So what is it? So these functions, if you look at they are of absolute value 1 everywhere. So you can't integrate them over Z, meaning sum of squares is going to be infinity. So characters are not in L2 of Z. In particular, there is no meaning to orthonormality. Okay, so there's no sense of orthonormality. Still, I mean, so engineers often write this a formal statement such as EVT and EVS equal to delta TS. So formal state, this is a purely formal statement, okay? So is actually useful in the sense is of some value. I mean, of intuitive value, you cannot write it. It's not mathematically meaningful, but you have to, it can be made sense of, has to be made sense of in an indirect way. So for example, but pretty much all the issues in Fourier analysis on Z or R will be like this. These are not exactly orthonormal, right? I mean, these are functions. These are not even L2 functions. So what the hell does that mean? It doesn't make sense. So what we can do is, one way of making this precise is, if you look at minus n to n with uniform probability measure. That is normalized counting. There you can look at in this, let me just write n, is by definition 1 over 2n plus 1. That's the number of elements here. k equals minus n to n, EVT of k, EVS of k bar, which is e to the ITK e to the minus ISK. Which, what happens to this? This converges. What happens to this? This converges to 0 if t not equal to s, and is always equal to 1 if t equal to s. If t equal to s, all these are 1 and you have 2n plus 1 things, the total is 1 always. What happens if t not equal to s? This is an oscillatory sum, and you know, in fact, you can just do a geometric series. I mean, this you know, in fact, it is given by the Dirichlet kernel. So you can see that this is actually, so what will this give you? So this sum will, in fact, if t is not equal to s, you can show that this will actually go to 0 as n goes to infinity. Okay. So you just, this is actually the Dirichlet kernel. I'll just not write it again. So in this sense, this actual formal statement is actually a useful thing. It may not be just this that you have to use, but you have to always approach it indirectly. And it's many a time electrical engineers write this kind of statement, and it's of good value for intuition. Although it's mathematically, you have to be always more circumspect in how you interpret it. Okay, so that's the general point. Okay, so now let me go back and define Fourier transform. So this is okay. So now let me go back and define Fourier transform on integers. If f is a function from integers to complex numbers, define. So I have to say what kind of functions, but for a moment, let's see f hat from the dual, right? The dual is now characters are indexed by t by f hat of e to the I theta is, formally you have to take inner product of f with that evaluation theta, which is sum over n in z f of n ev theta of n conjugate, which means f of n e to the minus in theta. So this is how you define. For what functions will it make sense? So it's not any z to c. So this is well defined. So if f is in L1 of z, that is summation f of n is finite, absolutely, then this is well defined. This is absolutely summable and you can define it, right? So it is well defined. But what about L2 functions? Not necessary for functions in L2 of z. So this is somehow complementary to what happened with the circle group. If you go back to the circle group, at first we were interested in Fourier transform for L2 functions, but we could go further and define it for L1 functions, and L1 is larger than L2. Therefore, that subsumes L2. And we went further and defined it for measures. But when you go to Z, it is naturally well defined for L1 functions, but L1 doesn't contain L2. Okay, so that is something to keep in mind. This is an infinite space, infinite measure space. So L1 of Z does not contain L2 of Z. Okay, so that is the problem. So it doesn't make sense. So Fourier transform is not well defined for L2 functions, but for measures it is okay. So we'll have to make sense of this, but in between let me write a measure on Z is of the form what is a finite measure on the integers? It is always of the form some atoms will be there, right? So let's write it as f of n delta n. And in Z with, okay, if I want positive measures, f will be non-negative and f in L1 of Z. Okay, so you can define, so you're back to, so measures on Z, finite measures on Z can be identified with L1 functions. So mu hat is defined as f hat. Okay, define. So for measures oppose no problem. Once on L1 of Z, measures on Z are same as L1 functions, okay, with non-negativity condition. So for measures we can define. So that part is not there. But how do you define Fourier transform for L2 functions? This is not so clear because there are functions which are in L2 which are not in L1. So how do you go about doing that? This is something that is non-trivial and I want to just explain. But before that, are there any questions? Is it clear what I'm doing? Is it too trivial? Okay, so now let me explain how one defines Fourier transform for functions in L2 of Z. It's not at all clear from this. So what we have to do, it has to be approached rather indirectly. So let's do that slowly. So first we have to analyze Fourier transform on L1. So what we should do is suppose f is in L1 of Z intersection L2 of Z. So let's take a function which is example f vanishes outside a finite set. So if you take a function which vanishes outside a finite set, then such a function is in both L1 and in L2. Okay. So for that, Fourier transform is well defined. Because it's in L1, so we can define this. Okay, so we can define this. So what we claim now, f hat is in L2 of T and its norm in L2 of T is the same as the norm of the original function in L2 of Z. Okay, so we don't have Fourier transform defined yet on L2 of Z. So we have to consider functions in L1 intersection L2. Claim is then the Fourier transform is in L2 of T and this equality holds. Sorry, there is a phone ringing. So how do we prove this? So let's prove this claim. So it is not difficult. So we just have to look at, so consider, so what is it? So we have to look at f hat L2 norm squared, right? So f hat of theta or e to the I theta, I keep switching, is defined as sum over n in Z, f of n e to the minus I n theta. That's how I define. So if I take square, is I get a double sum over m and n in integers, f of n, f of m conjugate, e to the I minus I n theta plus I m theta. So I into m minus n theta. Okay. So you look at this. So now you integrate. So first let's not worry about the, so let's justify everything at the end. So let's just integrate and freely interchange the sum and integral. So this is the integral over t, sum over m and n in integers, f hat of n, f hat of m, conjugate e to the I m minus n theta, and then we have to do d theta over 2 pi, which is okay if so. This is a question, but let's just interchange these sums. Then you have, what do you have? This comes out f hat of n, f hat of m conjugate, and then you are left with the integral over the circle of e to the I into m minus n theta d theta over 2 pi. Now you know that this is 0 if m is not n and 1 if m equal to n. So what you get is so when m is n, you get just f hat of m square, which is just the L2 norm squared of f. Okay, so this claim is not difficult. You just follow the definitions. Only thing we have to justify this interchange of sum and integral. How do you justify that? Any suggestion? How would you justify this? Okay, so it is, so you have to just see that. So let's look at n m theta going to f of n, f of m conjugate e to the I into m minus n theta. So this is a function from z cos t. Okay, n and m are integers and theta is a point on the circle. So let's look at this function from that space into this. Point is, this is absolutely integrable. Is in L1 of this product space. Why is that? You just take absolute value and sum, because so if you, what is the integral here? It's the product thing, right? So which means sum over m in z. The first argument is n, sum over n in z, and then integral over t with respect to d theta over 2 pi of the, if you take the absolute value of this thing. This is nothing but everything is okay. This is just 1 and that integrates to 1. This comes out is just sum over n, sum over m, f of n, f of m absolute value, which is just the L1 norm of f squared. Okay, it's not L2. Just assuming f in L2 was not enough. F is L1 that is being used here. So hence, so this is integrable. Therefore, you can use Fubini's. Fubini's theorem allows interchange. Of sum and integral. Okay.
Sir,
Huh.
can't we say directly because the sum is actually finite? Because A vanishes outside finite sets?
No, I said as example. Yes, if you assume
Okay, I
f
see.
is a finite, yeah, that is right. We could simplify and do it that way. But even there, the integral, okay, yeah, if you do that, then the justification is way simpler. You are perfectly right. I said that as an example. Oh, by the way, yeah, I said that as an example, but actually I was working under the assumption L1 intersection. So let's
I
put
see.
this as
And sir, that f hat, is that f hat or just f hat in f hat m, or just f of m and f hat?
confused here. So this all there is no hat, right? I mean, sorry, function is on integers. This is f hat. Here there is no f hat. Sorry, I made a mistake. F hat is this. F is a function on integers and f hat is a function on the circle group. So f hat of theta squared is this squared. So here there is no hat in any of these things. So this is also not a hat, and this is, in the end I got the correct thing, but there is no hat in any of these things. Is okay? Sorry for that confusion.
Yes, sir.
Yeah. So yeah, if you work under this weaker assumption, I mean, then it's okay. But under L1 intersection L2, you need this Fubini type. You need some justification. So this proves the claim. So what we have shown is that for Plancherel's theorem holds for F in L1 intersection L2. Okay. So, but most importantly for me, what this is that, so L1 intersection L2. So now let me say how to extend Fourier transform to L2. This is a useful thing to know. This is how it works in the real line also. So how to extend L2 of Z. So we note that L1 of Z intersection L2 of Z is dense in L2 of Z. In fact, that's why I had written this. Functions which vanish outside a finite set, they themselves are dense in functions vanishing outside a finite set. Of course, the finite set is not fixed. Every function that with a finite support is what I mean, are themselves dense in L2, also in L1 and all that. Okay, so these are themselves dense. So this is dense. And what we have seen from above claim, the Fourier transform, which is defined on L1 and in particular on the intersection of L1 with L2, that maps into L2 of T. That's what we have seen is an isometry. Isometry means it preserves the distances and hence uniformly continuous. Okay, what do I mean uniformly continuous? The distance between the Fourier transforms. So you take two functions here. Okay, so we take L2 metric. Okay, so what is uniform? I should say what is the metric on both sides with L2 metric. On left. So if we take this L2Z metric here and L2T metric here, then it's an isometry. So what we are saying is that, I mean, so the distance between the Fourier transform of two things is the same as the distance between the this for F and G in L1 intersection L2 of Z. So therefore, this is actually, I mean, of course, if it's like this, it's uniformly continuous. Now you have a uniformly continuous Fourier transform is a uniformly continuous function on a dense subset of L2 of Z. And here, then you can extend it, right? Why is that you can extend? So anytime you have a uniformly continuous function on a dense subset of what? Why is it that can you always do that? If you have a dense subset and a uniformly continuous function, then you can extend it to the whole set. So by general fact, so maybe I give it as exercise. So let's say X, Y are two metric spaces. I mean, this is something that you would have seen in basic analysis class, but you may or may not remember. So let's take a function f from X to Y. So these are metric spaces. So and let's say Y is complete. And I take a dense subset here. Okay, so this is all set up. Okay, so f is a function from X to Y, two metric spaces. D is a dense subset of X and Y is assumed to be complete in the metric, in whatever its metric. If f is uniformly continuous, on D, then f extends in a unique way to a continuous function on X. That is, there exists a unique G from X to Y continuous such that G restricted to D is same as F. Okay, so I got originally actually F may be defined only on D actually. So maybe I got it slightly badly. Okay, it doesn't matter how you define it outside D because all that matters is that G agrees with F on D. Okay, so this is something you would have seen. So this is how you can extend a function. Because of that, now you extend. So because of this, now you see that we have proved how to define Fourier transform. So because of this, Fourier transform extends and it is easy to see that it will retain the isometric property as an isometry of L2 of Z into L2 of T. So this part actually, so here it will be in fact onto, but not yet clear. Onto, but we'll see. So this is not yet clear that it is onto, but it will extend as an isometry of L2 of Z into L2 of T. So this is how you define Fourier transform. So that extended thing will still denote Fourier transform. Okay, this is the definition of Fourier transform on L2 of Z functions. You start with L1 intersection L2 and extend it to L2. So you have not changed the definition for L1 functions. Okay, so for functions which are in L1 intersection L2, the definition remains. This is an extension. So you have extended Fourier transform to L2 functions. Is this okay? Any questions here? Okay, so this is a bit, I mean, it's a little non-trivial. If you have never seen it before, if you have seen it before, okay, so it's all easy, but otherwise, this is a little non-trivial point that you cannot define when you have working with integers. You don't define Fourier transform directly for L2 functions. You can define for L1, then extend it to L2. Okay, so that's how it works. Okay, what time is it? Okay, it's almost the end of the time. So let me say further. In fact, one can go further. Maybe I give it as exercise. Oh, maybe I will tell you, in fact, because this is also a feature that works in general in real life. Okay, so Fourier transform on I'll remark later. So further, one can even go further. And define Fourier transform on LP of Z for P between 1 and 2. Already we have it at 1 and 2. Okay, for L1 functions we have, for L2 functions we have, but uh, for functions in between also we can do. So maybe I'll just give it as exercise here. So I'll give one proof and give exercise later. How? This is because Fourier transform we have seen is mapping L1 of Z to L infinity of t. Okay, with so I'll just write Fourier transform of f with operator norm. I'll write operator norm less than equal to this is because of the thing that I said here, that on L1 functions we define the Fourier transform. What did I say? Where is it? Didn't I say it somewhere? The L infinity business. Where did it disappear? Okay, actually, okay. Now I don't see where on earth I wrote it. Okay, so
I think it was on the previous page, no?
oh, for the other side I got. Okay, so point to note here is that I can let me just extend it here. It's well defined. So for L1 functions, we had defined Fourier transform like this, and in fact, we see that f hat of e to the I theta pointwise is bounded by mod f of n, right? So that is f hat in L infinity of t is bounded by norm of f in L1 of z. Okay. So the L infinity t norm of L2 of f hat is bounded by L1 norm of f. So that's what I go back to here. So that's what I am saying. L1 to L infinity has operator L1 z to L infinity t has operator norm less than equal to 1. And then also we have Fourier transform from L2 of z to L2 of t. We have already seen also has operator norm. It's equal to 1. Let me just write less than equal to 1. Operator norm is 1. In fact, in both cases, it's 1. Hence, you can apply Ries-Thorin theorem. And extend Fourier transform. What it does is it extends it to from LP of Z to, so here 1 goes to infinity, 2 goes to 2. So what is, as 1 goes from 1 to 2, I mean as p goes from 1 to 2, the other side exponent will go from infinity to t. It will be conjugate exactly. Okay, LP dash of t. Look back at the Fourier interpolation theorem where 1 by p plus 1 by p dash is 1. That's the conjugate exponent. And it's an extension, meaning that if you, it's an extension because if some function is in the intersection, for example, in L1 as well as LP, then it will agree with the original. So this is the Fourier interpolation theorem. So that's how you can extend it to all LP functions also. You won't be using this. I thought I would mention this. It's an important point to. So let me give an exercise of a different way to do it. So take a p in 1 to 2 and f in LP of Z. Actually, this is very general, but let me write in the context at hand. Show that there exists G in L1 of Z and H in L2 of Z. So this has to do with the fact that Z is an infinite measure space. So LP is not contained in L1, it's not contained in L2. Okay, there is no containment there. Oh, sorry. Sorry. 1 second. Maybe I'm making a foolish point here actually. LP actually on Z. On Z the monotonicity goes the. Does it go the other way?
It's 1 o'clock.
Goes the right way, no Manju. So L2, there is nothing here.
Right? I mean, if things are.
So L2 is contained in L1.
Sorry, L1 is contained in L2. So actually then there was no point. Actually this is actually meaningless because once.
No, other way.
Actually all this is meaningless. Okay, in real line this makes sense, but actually this whole thing can be ignored. Because actually, this is, while this is true, it is all a bit of a. I mean, I didn't think through. I thought that it will just give a motivation for real line, but there is a difference between real line and integers. I apologize for this. I should have thought through, because for p less than 2, you know, LP contains L2, right? LP is contained in L2. Shrikant, this is what you said, right? Lower one will be contained in.
No, the higher one will be L2 is contained in L.
No, L2 is not contained in L1. That was the problem, right? So, for example,
1 by n will be contained in L1, but not in L2, but not in L1.
Yeah. So, if you look at this sequence, belongs to L2 of Z, but not in L1 of Z. So, yeah, but if it's in LP, then it is in L2. Yeah, so actually I don't need all this operator, the Fourier and so on. So for the silly point, LP is contained in L2 because if P is less than 2. So you automatically, once you have defined it on L2, you have also defined it on LP for P less than 2. This will be a non-trivial point in when you go to R, real line. There is no containment in either direction. It's not a finite measure space and it's also not discrete like this. Because of that, there is no containment in either direction. And there, this point will be non-trivial that you can extend it to LP. But okay, I should state it there. Sorry about this. All this is actually meaningless. It's erased. Okay, so this way, do I have any time left? Okay, I am already done. So what I will do next time is, so with this.
That's right. That's what I meant. Okay.
So this is right. So summable means square summable, right? So yeah. Okay, so what I will do next is, okay, so next time I will just wrap up with the points of, I'll just wrap up the duality. So now you have Fourier transform on Z and Fourier transform on T. And I will just repeat the Fourier inversion. It's a kind of the duality picture will be sort of complete here once we do this. And after that, I will go to the real line and develop the theory, and then maybe tell you the theory in the locally compact abelian case. With that, I will probably this week or maybe one more lecture, I will finish the abstract theory, and then we can go on to many applications. There are many interesting applications. I have a few weeks of time, I believe, for that. Okay. So I will now stop.